Welcome to Space Oddities, and especially welcome to this Astronomy Basic. Today I want to talk to you about the Sun and take a glimpse into the heart of our solar system. The Sun, our celestial neighbour and the centre of our solar system, is a remarkable celestial body. It is a star, a massive ball of hot plasma, a state of matter where atoms are stripped of their electrons, creating a hot, electrically charged gas. The Sun is primarily composed of hydrogen and helium that radiates immense amounts of energy, influencing the Earth's climate, shaping our seasons, and providing the essential light for photosynthesis, the process by which plants convert light into food. The Sun's immense gravitational pull holds the planets in our solar system in their orbits. Understanding the Sun and its workings is crucial to comprehending our place in the universe and the delicate balance that sustains life on our planet. Here is some more essential characteristics of our Sun. Mass. The Sun is about 1.3 million times more massive than Earth, and its diameter is about 109 times larger. Basically, what that is saying is the volume of the Sun, you could actually fit 1,300,000 Earths into it. And with it being 109 times larger, it means across the equator of the Sun, you can line up 109 Earths. Composition. The Sun is composed primarily of hydrogen, about 72%, and helium, about 26%. Trace amounts of other elements, including oxygen and carbon and iron, also exist. Temperature. The Sun's core is incredibly hot, reaching temperatures of over 15 million degrees Celsius, which is 27 million and 32 degrees Fahrenheit. The intense heat is the source of the Sun's energy. Energy production. The Sun's energy is generated through nuclear fusion reactions, a process in which hydrogen atoms are fused into helium atoms, creating immense amounts of energy. Radiation. The Sun emits a vast amount of energy in the form of electromagnetic radiation, including visible light, ultraviolet light, infrared radiation, and radio waves. Gravity. The Sun's immense gravity holds the solar system together, keeping the planets and other celestial bodies in their respective orbits. So, how does the Sun work? Nuclear fusion, the Sun's power source. At the heart of the Sun lies the source of its incredible energy output, nuclear fusion. This process involves the merging of hydrogen nuclei into helium nuclei. In this process, two hydrogen nuclei, or protons, collide with such a force that they fuse together, forming a helium nucleus, or an alpha particle, and releasing a neutrino and a gamma-ray photon. This process releases a tremendous amount of energy, accounting for the Sun's luminosity. The fusion reaction in the Sun's core is a continuous process, with approximately 620 million metric tons of hydrogen being converted into helium every second, releasing vast amounts of energy in the form of heat and light, which is then transported outwards through the Sun's layers, ultimately reaching the photosphere and escaping into space. Energy transfer. The energy generated in the core travels outward through two main processes, radiation and convection. Radiation involves the emission of electromagnetic waves, while convection involves the movement of hot plasma carrying energy from the core to the surface. The corona. The Sun's outermost layer, the corona, is a highly ionized plasma that extends far beyond the visible surface. It is the source of solar wind, a stream of charged particles that permeates the solar system. Activity cycles. The Sun's activity, including sunspots, solar flares and coronal mass ejections, varies in a cyclical pattern, with an average period of about 11 years. These events are driven by changes in the Sun's magnetic field. Now let's take a look at the composition and structure of the Sun, the solar interior. The Sun's structure is remarkably intricate, encompassing a vast range of layers and phenomena that contribute to its overall functioning. From the core, where nuclear fusion powers the Sun's energy output, to the outermost layers that unleash solar flares and coronal mass ejections, each component plays a crucial role in the Sun's dynamic nature. In the center, we have the core, the Sun's densest and hottest region, where nuclear fusion reactions relentlessly convert hydrogen nuclei into helium nuclei, releasing immense amounts of energy. The Sun's core, located at its center, is the hottest and densest part, reaching temperatures of up to 15 million degrees Celsius. That is followed by the radiative zone. Surrounding the core, the radiative zone acts as a vast heat transfer medium, transporting energy through the Sun's interior by radiation in the form of photons, similar to how heat travels through a pot of hot water. This is then followed by the convection zone, located above the radiative zone. The convection zone carries the movement of hot plasma upwards and cooler plasma downward through convection currents. The Sun's surface. The photosphere is the visible surface of the Sun, the layer that we see when we look at it with the naked eye, where radiant energy escapes into space in the form of light and heat. The photosphere is characterized by a granular texture, with bright granules representing rising hot plasma and dark intergranular lanes representing sinking cool plasma. It is a thin layer, only about 100 kilometers thick, but it is the source of most of the Sun's energy that reaches Earth. The photosphere is a turbulent region with frequent convection cells, which creates the familiar granulation pattern visible on the solar surface. Above the photosphere comes the chromosphere, the solar atmosphere, a thin reddish layer above the photosphere extending up to about 10,000 kilometers. The solar atmosphere consists of several layers extending outwards from the photosphere. The chromosphere is a layer immediately above the photosphere, is a thin reddish layer that becomes visible during total solar eclipses. It is the source of solar prominences, towering structures of hot plasma that can extend vast distances from the Sun's surface. The final layer is the corona, a superheated atmosphere. The corona is the outermost layer of the Sun's atmosphere, a vast extended region of extremely hot plasma that can reach temperatures of millions of degrees Celsius, extending far into the solar system. It is only visible during total solar eclipses, as its brightness is far fainter than that of the photosphere. It is the source of solar flares and coronal mass ejections. The corona is also the source of the solar wind, a continuous stream of charged particles that flows outwards from the Sun and interacts with the Earth's magnetic field, creating auroras and influencing space weather. Let's look how the Sun influences the Earth. The Sun's influence extends far beyond its visible presence in the sky. Climate and weather. The Sun's energy drives Earth's climate and weather systems. It heats the atmosphere, which in turn heats the oceans, driving ocean currents and influencing precipitation patterns. Photosynthesis. Plants rely on sunlight for photosynthesis, the process of converting sunlight into chemical energy. This process is essential for sustaining life on Earth. Space weather. The Sun's activity can affect Earth's atmosphere and magnetic field, disrupting radio communications, affecting satellites, and causing auroras. Solar radiation. The Sun's radiant energy is absorbed by Earth, providing warmth, which helps maintain the Earth's habitable climate. Solar wind. The Sun emits a constant stream of charged particles called the solar wind, which can affect Earth's magnetosphere, influencing communication systems and satellite operations. Coronal holes. These are sources of enhanced solar winds. Areas of low magnetic activity on the Sun's surface allows more of the energetic particles created by the Sun to escape out into the interplanetary medium. Solar flares. Sudden bursts of energy from the Sun, capable of disrupting power grids and radio communication. Coronal mass ejections. Large expulsions of plasma from the Sun's corona, potentially causing geomagnetic storms that can disrupt power grids and high-frequency radio communications. So let's take a closer look at some of these events that happen on the Sun. Sunspots are phenomena on the Sun's photosphere that appear as temporary spots that are darker than the surrounding areas. The surface of the Sun, the photosphere, is about 10,000 degrees Fahrenheit, while the umbra is about 6,300 degrees F. They are regions of reduced surface temperature and are caused by concentrations of magnetic flux that inhibit convection. In other words, they prevent the hot plasma from rising to the surface in that area due to convection. Hence, a lower temperature is seen in that area. Sunspots appear within highly active magnetic regions, usually in pairs of opposite magnetic polarity. Their number varies according to the approximately 11-year sunspot cycle. A typical spot consists of a dark region called the umbra, surrounded by a lighter region known as the penumbra. Individual pairs of sunspots or groups of sunspots may last between anywhere from a few days to a few months, but eventually will decay. Also, sunspots expand and contract as they move across the Sun's surface, with diameters ranging from 16 kilometers, which is 10 miles, to 160,000 kilometers, which is 100,000 miles. Indicating intense magnetic activity, sunspots accompany other active region phenomena such as coronal loops, prominences, and reconnection events. Most solar flares and coronal mass ejections originate in these magnetically active regions around visible sunspot groupings. Solar flares usually take place in active regions, which are regions on the Sun marked by the presence of strong magnetic fields, typically associated with sunspot groups. As these magnetic fields evolve, they can reach a point of instability and release energy in a variety of forms. These include electromagnetic radiation, i.e. X-rays, which are observed as solar flares. Solar flares are large eruptions of electromagnetic radiation from the sun lasting from minutes to hours. A sudden outburst of electromagnetic energy travels at the speed of light. Therefore, any effect upon the sunlit side of Earth's exposed outer atmosphere occurs at the same time the event is observed. The increased level of X-ray and extreme ultraviolet, also known as EUV, radiation results in ionization in the lower layers of the ionosphere on the sunlit side of the Earth, and this will cause radio interference or even blackouts. Flares occur in active regions and are often, but not always, accompanied by coronal mass ejection, solar particle events, and other solar phenomena. A coronal mass ejection, or a CME, is a significant ejection of magnetic field and accompanying plasma mass from the Sun's corona into the heliosphere. CMEs are often associated with solar flares and other forms of solar activity, but a broadly accepted theoretical understanding of these relationships has not been established. If a CME enters interplanetary space, it is referred to as an interplanetary coronal mass ejection, or ICME. ICMEs are capable of reaching and colliding with Earth's magnetosphere, where they can cause geomagnetic storms, aurora, and in rare cases damage to electrical power grids. The largest recorded geomagnetic perturbation, resulting presumably from a CME, was the solar storm of 1859, also known as the Carrington event. It disabled parts of the newly created United States telegraph network, starting fires and shocking some telegraph operators. Coronal holes appear as dark areas in the solar corona in extreme ultraviolet, which is EUV, and soft X-ray solar images. A coronal hole is a temporary region of relatively cool, less dense plasma in the solar corona, where the Sun's magnetic fields extend into interplanetary space as an open field. Compared to the corona's usual closed magnetic field that arches between regions of opposite magnetic polarity, the open magnetic field of a coronal hole allows solar wind to escape into space at a much quicker rate. This results in decreased temperature and density of plasma at the site of the coronal hole, as well as an increased speed in the average solar wind measured in interplanetary space. If streams of high-speed solar wind from coronal holes encounter the Earth, they can cause major displays of aurora. Near solar minimum, that is when activities such as coronal mass ejections are far less frequent, solar wind streams are the main cause of geomagnetic storms and associated aura. All these events create various energy levels and temperature ranges, which stretch all the way across the electromagnetic spectrum. So to be able to view all these events, we need to look at the Sun in different wavelengths. In this image on the left you can see the Sun in visual light, and you can just see the southern spots. On the right is an ultraviolet image, and you can see far more detail and events that are happening on the actual Sun's surface. This slide shows images of the Sun all taken at the same time and at different wavelengths. They range from visual light all the way up to X-rays. You can see every image is different. It is showing us a different layer of the Sun, with all the different activities and the temperatures that are happening within those regions. If you look underneath, you can actually see what is being exposed by each wavelength. The Sun is a dynamic celestial body, constantly exhibiting various phenomena related to its magnetic field and the movement of plasma within its atmosphere. These phenomena, including sunspots, which are dark blemishes on the photosphere that are cooler than the surrounding plasma, solar flares, sudden bursts of intense electromagnetic radiation and high-energy particles, and coronal mass ejections, CMEs, large eruptions of magnetized plasma from the corona that can travel vast distances into the solar system. The Sun's future. Evolution. The Sun is a middle-aged star, having existed for about 4.5 billion years. It will continue to shine for billions of years more, but as it ages, its luminosity will increase, and its surface will become more active. Red giant phase. In about 5 billion years, the Sun will enter its red giant phase, expanding to engulf Mercury and Venus. Earth will likely be vaporized, and life as we know it will cease. White dwarf. After the red giant phase, the Sun will collapse into a white dwarf, a small dense star with very high surface temperature. It will slowly cool over time until it fades into darkness. Conclusion. The Sun, our celestial neighbour and the source of life on Earth, is a magnificent celestial object that continues to amaze scientists with its complex structure and dynamic behaviour. Its immense energy sustains life on Earth and shapes the dynamics of our solar system. Its energy powers our planet, shaping our climate and influencing our daily lives. As we continue to study the Sun, we uncover more about its mysteries, gaining a deeper understanding of the universe and our place within it. If you feel inclined to delve deeper into the workings of the Sun, or just to learn a bit more about space weather, I can highly recommend Dr. Tamitha Skov on YouTube. Or, if you just want to follow the space weather or the Sun's activity, here are a few apps that are all free for you to follow. Well, I hope you enjoyed that, and hope you learned something. And I'll see you again next time. Everyone take care. Bye.